So let's get started today's session. So it's a great pleasure for me to introduce our speaker, Professor Immanuel Bloch. Professor Bloch is Scientific Director at the Max Planck Institute of Quantum Optics, Garching, and a Professor for Experimental Physics at the Ludwig Maximilian University. He is also one of the spokespersons of the Munich Center for Quantum Science and Technology. Professor Bloch obtained his PhD in physics in 2000 from Ludwig Maximilian University. His research focuses on quantum many-body systems, quantum simulations, quantum information processing, and quantum optics. He received many awards and honors. To name a few, he received several awards and honors. To name a few, Gottfried Wilhelm Leibniz Prize of the German Science Foundation, the German National Merit Medal in 2005, the International Commission of Optics Prize, the Senior Prize for Fundamental Aspects of Quantum Electronics and Optics of the European Physical Society, the Corbett European Science Prize, the Senior BEC Prize, the Harvey Prize of the Technion. So with this brief introduction, may I invite Professor Bloch to present your talk.
All right, thank you very much for the kind invitation to lecture here in this school. Of course, we're doing great to do this in person, but hope we can do this soon again. So yeah, it's just a bit formalities. Maybe actually you can also, I have the participants window also open. So if you have questions, we just said we can ask these questions throughout the talk. So I try to keep an eye, my host tries to keep an eye on what's going on in the chat. And if you have a question, raise your hand or just speak up. So it should be kind of more interactive. And then you can also have a chance to slow down my speed if I'm going too fast. It should explain things a bit better than I did. Okay, so I want to start talk today and giving you an outline. Did you see the slide change actually? Did the slide change? Sometimes it doesn't change. Yes. So I want to talk about atoms and optical lattices and fundamental many-body physics we can do with these systems and introduce you to the system that we're looking at and also tell you a little bit about the physics we're doing there. And then we start with some very simple phenomena. And then we work our way up to more complex phenomena to show you also a little bit of the flavor of where research is standing today. Maybe I have also a chance in the second part tomorrow to talk a little bit about new quantum optics, light matter interfaces that you can actually realize with these systems. So there's actually also some quantum optics applications in studying these systems. So you've seen already quite a few talks, and so you've probably heard about these many-body quantum systems, interacting many-body quantum systems that really, for me, when I got started in this field, were, the motivation was to really understand these complex systems better, to learn more about their behavior from a fundamental physics point of view. But of course, now all these systems have also become incredibly important from a technological point of view, from a metrological point of view. And there's this whole new field of quantum technologies that has been emerging. And so now we've seen this fantastic new artificial quantum systems come up made out of, for example, individual atoms or ions or photons or solid state systems, which allow us to probe quantum matter or quantum many-body systems in completely new ways. And you already heard quite a few examples in this talk, in this conference, in this school. And I want to today add a bit more on these crystals of atoms, these atoms that are stored in light fields in these systems. So why, I just want to recap again, why it's so difficult to calculate the behavior of such systems. And of course, by now, you probably also know that the real problem here is that the exponentially growing Hilbert space poses very big problems for classical computers to solve some of these problems. And with every particle or spin we add to a system, we have to double the amount of memory that we need even just to store that, for example, quantum state in the memory of that computer. But of course, one has to be a bit careful with this statement because they're very good theoretical physicists in solid state physics that derive approximation techniques that capture very well the behavior, for example, of ground states, that they find efficient numerical descriptions, for example, for the ground state of a certain physical system. And the reason why it works is because the ground state of this physical system typically only occupies a very, very small part of the entire Hilbert space, which would be my entire screen. So of course you have to find this good approximation, this good numerical technique to describe this small part in Hilbert space. But if you can have that, then you actually have a very good also classical computation possibilities for calculating behavior of matter in the system. We will also talk about dynamical experiments, where in dynamics, in quantum dynamics, very often you really explore the entire Hilbert space. And this is, of course, why dynamics is often the hardest problem from classical computational point of view, and maybe the most interesting also from a quantum point of view to study, because actually it gives us access to phenomena that we don't have access to in the classical computational scope. So the system we're going to look at here are these artificial quantum systems. Actually, you see here is very small. These dots here are real atoms in a real system. So imagine this would be a real material with angstrom size separations. And what I'm going to show you that these artificial quantum systems that we're going to talk about, like these atoms and lattices, allow us to scale up this matter by a factor of 10,000. So now suddenly all the distances here between the atoms are not on the angstrom scale, but on the micrometer scale. And that, of course, now has dramatic consequences, because now we can look into these systems, we can probe their behavior, we can get a microscopic view of what's going on in these systems, and also control single atoms in these systems. So just to connect to other platforms you might have heard about in the series of this school, there's been, of course, the ion traps, where you have charged ions held in a Pauli trap, for example. And you can have like 50 ions, for example, stored in this Pauli trap. You can also address individual atoms individually. You can entangle them by making use of the motion of this ion trap, of the crystal, of the ion crystal stored in this ion trap. And basically what you are making use of here, you're making use of the long-range interactions via Coulomb interactions between these ions in this ion chain. There's this other platform that has become very prominent. This is this optical tweezer platform, where you basically store or trap individual atoms in individual focused laser beams and make use of Rydberg interactions to basically make these atoms interact with each other. That's something, for example, Tilman Fau probably talked about in his talk. And today I want to actually focus more on this third aspect of these optical lattices, which allow us to create different type of optical trapping potentials simply by interfering laser beams. So here's the picture of how this works. So you take one laser beam coming from the left, one laser beam coming from the right. Let's say this laser has 850 nanometer wavelength, and it's a coherent light field. Then you interfere those two beams, and you, of course, get an optical standing wave. The period of this optical standing wave now is just half the optical wavelength if you interfere them under 180 degrees. And basically, by interfering laser beams under different angles, you can realize any kind of lattice structure you want. You can have square lattices, hexagonal, triangular lattices, Kagome lattices, super lattices, anything you want. So let me show you a few examples of this from the labs of Ted Hensch that he took in his labs in Munich. So he did a very simple experiment. Namely, he took a piece of cardboard and punched two holes into this cardboard, and took a laser beam and expanded this laser beam to a large size and sent the laser beam through these two holes. And after these two holes, he placed a lens to refocus the beams. And then, of course, you all know what happens if you have these two apertures, two openings, and you have the lens that combines these two beams. You get interference of these two fields. And this is what you see here under the microscope objective. This is the interference pattern from these two light fields emerging from these two holes that you record on your screen, for example. So you see this nice periodic structure, which is the optical lattice that is created by interference of light fields. Now, if you take three openings, you already see you get this nice triangular hexagonal lattice. Or if you take 5 openings, for example, you see this beautiful quasi-crystal type interference pattern emerge with a 5-fold symmetry reflected in this 5-fold symmetry of these openings, also now reflected in the real space interference pattern. So again, this is really the real light field interference pattern recorded from these 5 beams. It's not a mathematical calculation or something. It's real interference, a real physics phenomena. And you can already see from this beautiful picture how perfect these crystals are that you can create by interference of light. So you can really realize light crystals of light that have no defects, that are very, very controlled potentials, where we can control the depth of the potential, for example, by simply controlling the intensity of these laser beams. And now our challenge is to basically put atoms into these crystals of light. And the reason why this works is because there's the dipole force in the interaction of the light field with the atom that allows us to create a trapping potential for the atoms. So if we only make the atoms cold enough, they will really see this intensity modulation of the light field as a trapping potential for the atoms. And now suddenly we've trapped atoms in free space, in vacuum, in this light crystal, and they're just held by these light forces interacting with the atoms. We can do this, as you'll see, with up to a few thousand particles in the systems, and we can do this with spins. So we have like qubits there, but we can also do this directly with bosons or fermions in the systems. And that's going to be interesting, especially if we want to simulate the behavior, for example, of electrons in a real material with these systems, because the electrons in a real material are, of course, fermions. So what you want to know is, how do these fermions behave in periodic potentials and when they interact with each other? So by doing this with fermions directly, we don't have to pay this overhead of mapping this onto a qubit problem. Actually, if you want to have a look how these pictures were created, you can go to the YouTube channel of Ted Hensch. So he has this really nice YouTube channel, Superlaser123 is his username, and there are a lot of wonderful optics experiments shown there on how this actually works. I just want to share with you this nice, beautiful video where he actually shows how you can even trap more macroscopic particles in these light fields. So here you can see these laser beams. Let's say 4 laser beams that will be now overlapped, and we observe the interference pattern with a microscope objective. Now this is just 2 beams, and you see this nice stripe pattern. The reason why this moves is, of course, because the relative phase here is not being stabilized. Now you can see 4 beams interfering, so you see this 4-fold interference pattern. Again, the reason why this is moving is because the phase is not stabilized between them. That's something we don't want actually in the experiment. And now you can see actually small plastic beads, small plastic balls dissolved in water. And now when you turn on the light field, you can see something wonderful happening. You can see how these plastic beads lock onto the light field. They really want to align with the light. Well, have a look at this 2D pattern. Do you see how these small plastic beads want to lock onto the light field? It's because they really perceive this light field as this intensity modulation, as a trapping potential in which they want to lock into, just like into a classical egg cartoon where eggs want to lock into this egg cartoon. Now, of course, we're not doing this with classical particles. We're doing this with individual atoms. So we're not doing this with plastic beads, of course, but the same physics is at work between these plastic beads and the atoms. We're just using the quantum objects, the atoms themselves. Now, when we have trapped such atoms in these lattices, we want to have them interact with each other to make things a bit richer. And you've already heard about some of these interactions. I just want to recall them. You have the collisional interaction, when 2 atoms just come together on a single lattice site in this optical crystal. They collide, gives rise to a collisional phase shift, which gives rise to this collisional interaction. Then there's the dipolar interaction, which you heard about in the context also maybe of Rydberg atoms or polar molecules in Junier's talk. And then in Tilman Esslinger's talk, you probably also heard about these all-to-all interactions that you can realize by placing these atoms in these cavities. So these are different ways, different means of realizing kind of different types of interactions in these systems. Now, let me remind you again why we can study the physics of real materials in such artificial quantum matter, and which is extremely dilute. Right? I said you the separation between particles is on the micrometer scale, so it's really very, very large. So, of course, the reason is because in quantum mechanics, whether a system behaves quantum mechanically or a many-body system behaves quantum mechanically, the only thing that matters is the ratio of the de Broglie wavelength to the interparticle spacing d. So this would be the spacing between particles. This is the thermal de Broglie wavelength. And the only thing that counts in quantum mechanics is not absolute length scales, but relative length scales. So when this number is larger than 1, you're in the quantum degenerate regime, and you can expect collective quantum behavior of these particles. And now you can already see what that means if you go to these extremely dilute systems, these enlarged systems that I showed you, which have extremely dilute densities of 10 to the 14 maybe atoms per cubic centimeters, so about 100,000 times thinner than air surrounding you, then you have to, so the D is actually very large, the D is on the range of micrometer, then you have to make lambda also on the order of micrometer, and that means you have to cool the system down to a few nanokelvin to reach thermal de Broglie wavelengths, where this matter wavelength is so large, where the particles are so slow that the lambda is on the micrometer scale as this D, and then you reach this quantum degenerate regime. So for real materials, you of course at much higher densities, 10 orders of magnitude higher density, which is why you reach this quantum degeneracy already in the millikelvin, or even at room temperatures for some materials, because of this much higher densities in the system. All right, so then what we're going to apply is this technique of quantum simulation to learn about the behavior of a real material by studying these artificial quantum systems. And before going into specific examples of how we do this, I just want to show you the general idea behind this. So let's imagine you have a certain physical system that you want to understand better. Let's say somehow this high TC superconductor, for example. Then you want to first go to a theoretician and want to ask him, well, what's the model? What's your simplest model that could describe such a system that we should maybe test in the lab? Okay, then the theoretician will come up with a simple model Hamiltonian that we'll talk about in a second. Then you try to implement exactly this model Hamiltonian in the lab. You run your quantum simulator for a certain amount of time, you read the outcome, and then from the measurements, you try to learn about the behavior of the system, and you then feed back to the real system and see how would you have to change, let's say, a real material to give you this behavior. So what's also exciting is that you can also build systems which do not exist in reality, in the real world scenario so far, because you can have very different model Hamiltonians that you can maybe realize in the lab with these artificial quantum systems, like the atoms and the lattices, but you cannot realize in the real world yet. So that's also cool that you can really have access to new settings that are not accessible in the real world. So let me compare the approach of this analog quantum simulation to the digital quantum computing approach, because they actually both try to do a very similar thing. They try to, for example, calculate the time evolution or solve the ground state of a physical model. And in the analog approach I explained to you so far, you basically directly implement your model Hamiltonian in your system, the rule set by which these atoms behave with each other. In the digital approach, you have a few elementary operations like single and 2-qubit operations. And by concatenating these single and 2-qubit operations, you try to build up the time evolution of your desired model Hamiltonian. So this is nice, the digital approach, because in principle, you can build up any model Hamiltonian out of a universal set of single and 2-qubit operations. With the problem, of course, being that in practice, it might mean that you need a lot of qubits to realize this and a lot of time steps to gate operations to really fulfill this time evolution. The analog approach, on the other hand, has the disadvantage that you can only implement what you can implement in the lab. So you cannot have a universal way of studying any Hamiltonian. You're really limited to what you can do in the lab. However, if you can bring this Hamiltonian to the lab, if you can implement it, then you have a huge advantage for this system, because you can just run it for much longer times than you could do in any digital quantum computer approach. So you're not so surprised then if I put the two next to each other, quantum simulation, quantum computing, that they both really try to address very similar problems. And they have different advantages and disadvantages that I summarized here in this table for you. So the systems we are studying, these atoms and lattices, of course, have to all work in a vacuum chamber. We have to keep them cold. We have to keep them isolated from the rest of the environment. So we always have to do these experiments in ultra high vacuum chambers. So here's a picture of some of our systems, how they look like. You typically have such a glass cell, which is evacuated. You have coils where you have magnetic fields creating trapping potentials for the atoms. And right behind this wall here, which is all at room temperature, you have this nanokelvin object that we're talking about that we're going to study. So this is always amazing for me to see that you can realize this gas at nanokelvin temperatures just behind this wall here of glass. Now, another thing that's going to be important is that the system we create here is not connected to any reservoirs. So it's not connected to any thermal reservoir. So we have a truly isolated quantum system, which behavior we can study and try to, for example, test fundamental aspects of statistical physics, try to learn how actually do you reach thermal equilibrium if you're isolated from anything, right? Usually you equilibrate to a thermal equilibrium by bringing something in contact with something else, a reservoir, a thermal reservoir, for example. But here you have an isolated system, and you can ask, of course, how does statistical physics, how does thermodynamics work in such isolated quantum systems, and how does it fail? And you might say, well, isn't this an academic question? Well, it's an academic question, but it's of fundamental importance because, for example, the universe itself is an isolated quantum system that you want to study. Now, of course, when I say it's not connected to reservoirs, it's thermally isolated, this is not exactly correct. So let me try to be a bit interactive and ask you a few questions in the talk also. So why wouldn't this trapped gas of atoms be perfectly isolated from the environment? What could heat it up, so to say, in the long run? What could be a problem that you could see with this trapped gas of atoms here? Why is it not perfectly isolated from the environment? Does anybody have an idea? Background pressure, yeah, that could be a problem. And let's say it would be a good evacuated vessel. Radiation, yes, that's much better. So what problem could radiation cause? What kind of radiation would be a problem here? You can just unmute yourself also, and just so I get to know you also a bit personally and see your face. That's nicer for me also. Yes, so Dilip, there was black body radiation from the surrounding. Indeed, that's the right answer. So you have the black body environment, the radiation, and as you know, this black body radiation exchanges energy between the atoms and the environment. And of course, this will mean that eventually our atoms, by exchanging energy with the black body environment, with the black body radiation, they will come to thermal equilibrium. They will heat up from nanokelvin temperatures to room temperature. So why will this, do you think, what I can tell you is that this takes a long time, actually. Why do you think this takes a long time? What's the good thing that atoms have compared to molecules? For example, if you think of molecules, ultra-cold molecules or ultra-cold atoms, where's the advantage of why is this much less of a problem for atoms than for molecules? Do you have an idea why this could be much less of a problem? Yes, okay, great. Yeah, somebody else unmuted or okay. I see already in the chat, you're more in the chat room here. Yes, so excitation energies are higher in atom, that's true on one hand, and discrete energy levels placed far apart. Exactly. So the third answer is correct because molecules have many electronic states compared with atoms. It's all correct. Because basically there are very few resonant transitions with the blackbody radiation because the spectrum of an atom is so discrete, so sparse compared to the electromagnetic continuum of the blackbody radiation that you only absorb and emit on very few lines. And it takes a long time for this atom to equilibrate, come into thermal equilibrium with the blackbody radiation. And the answer with molecules is completely correct. With molecules, imagine a big C60 molecule. This thing can rotate, vibrate. It has a ton more of transition lines and can exchange energy much more efficiently with the blackbody environment. All right, very good. Great. So let's keep being interactive. So here's a picture in the lab. This is how this actually looks in the lab, how these experiments look. So you have typically a laser table here. You have a vacuum chamber here. This is all computer controlled basically. And we program the measurement sequence we want to do overnight. And then we come back in the morning and then we can read out the data and analyze the data and give it, for example, discuss it with our theory colleagues. So what kind of physics can you study? We'll mostly talk about condensed matter applications, but there are even applications to high energy physics that you can connect to. There's like crazy things like this quantum matter at negative absolute temperature that you can realize. So you can realize a gas of atoms at negative absolute temperature. You might have heard from your statistics physics course that you have negative temperature from magnetic systems, but how this works for moving particles is kind of a little bit intriguing. And you could ask your statistical physics professor how this actually worked to discuss this with you. What was interesting for us when we studied this is that it even led back to a discussion on the correct definition of absolute temperature. And it led us back to this original book from Gibbs, written in 1902, all pre-quantum era, where he lays out some of these foundations of statistical mechanics. And this is an excellent book, even by today's standards, in modern standards. This is a very, very readable book, and I highly recommend it to you if you want to learn a bit more about the history of statistical mechanics. There are phenomena, of course, in statistical mechanics. Why these insulating systems are interesting is that we can realize phases of matter that do not exist in the real world, as I told you. And one such phenomena occurs because these systems can be isolated from the environment, is the so-called many-body localization phenomena, where you can have an insulating state of matter we're connected to a extended thermalizing state of matter just in this isolated interacting many-body system. And there, this isolation from the world is actually very crucial. All right, the one problem that we're going to talk about a lot in my talk today, the lecture today and tomorrow, is this so-called Fermi-Hubbard model or Bose-Hubbard model, which describes atoms moving through this lattice from side to side. So they tunnel from side to side to this lattice. So imagine you have, remember, this is the sinusoidal potential, the standing wave we create by interfering the laser beams. And then if we want to ask, well, what is the potential of these, how's the energy landscape look like of this sinusoidal potential? Well, the first approximation, you can say, well, locally, you basically have like a harmonic oscillator. So you have a ground state, a first excited state, a second excited state in this harmonic oscillator. And then you can basically tunnel from one of these harmonic oscillator states to the next one by tunnel coupling, because this is a finite barrier of finite height and finite width. You can tunnel from your system from one of those ground states to the other ground state. And the coupling strength by which you do this, you can calculate this. I'm not going to show you this in this lecture, but we just denote this by this parameter T or J sometimes. We'll use this for different things, but let's say here it's T. This is the tunneling parameter, the tunneling strength that describes how strongly the atom is coupled from one side to the next. And H bar over T gives us basically the time scale it takes for the atom to tunnel from this left side to the right side. So there's the tunneling. This is like kinetic energy in the system. And then there's interaction energy in the system. And this interaction energy occurs when you bring two particles together on a single lattice side. And then I told you they collide with each other in this collisional interaction. And this gives rise to a so-called on-site interaction energy U. So you can now just think of this as the energy of the two atoms, not just being twice the ground state energy of the harmonic oscillator, but it's twice the harmonic oscillator ground state energy plus an extra amount of energy U, which is given by the interactions between the particles. And this U can be positive in the case of repulsive interactions. Then you have an increased energy cost when you want to put two on one side, or it can be negative if you have attractive interactions between two atoms. Then of course you would lower the energy when you put them on the same side. Okay. So this is the model. This is the so-called Fermi-Hubbard model. Very simple, but extremely complicated to solve, as we'll see, and we'll study a few examples of what kind of physics we can study with this system. All right, so before we go on to study that physics, let me show you a little bit more how we actually detect the particles, so how we probe them. So imagine now I have a following many-body state. So we're now looking at a many-body wave function of a many-body system, which I can generally write something like this, like you can see here. It's a superposition of different configurations of the atoms on the lattice that we create with this optical interference. So, of course, in principle, there should be complex coefficients in front of here as well, but we'll neglect these for a second. So imagine you have this many-body quantum state, which is the superposition of such configurations. And now let's imagine you had a camera. Let me give you a camera that can take a photo of such a system, where the resolution of this camera is good enough to observe a single lattice site. So it resolves single lattice sites. And let's say the camera is so sensitive that it can even detect single atoms or electrons in your many-body system and reveal the presence and tell you whether there's one atom or two atoms or zero atoms. So what happens if you take this camera and make a photo out of this psi? So what do you think? So I give you this camera and you take a photo now out of this quantum system. What's going to happen? What will you say is going to happen? Will you stay in this quantum state? Will it change? Yes, so René, the system will be modified by the measurement, indeed. But how will it be modified? What's going to be the outcome of this measurement? Yes, so you might obtain one particular basis state. That's right, or I wouldn't call it basis state, one of these, right? Or you're all right what you're writing in the chat. So basically what happens is that the wave function collapses onto one of those configurations, states that you see here. Onto which one it collapses, you don't know. That's completely random, this process. But of course, after you then take the photo, you might see this photo of the atoms. Okay. So now you've taken this photo, and let's say you take a photo again of the system. Well, then, of course, because it collapsed to this state, if you take another photo of the system, you will again see the same picture. So now in order to do another measurement, we really have to now recreate this many-body state psi. We have to go through all the creation sequence again to recreate it, and then do another measurement. And then in this other measurement, well, we're probably going to get another outcome of another configuration that we're going to see. And then let's imagine that I do this tens of thousands of times. And what you're going to get then is a probability distribution of these different configurations occurring in the system. So you have this configuration, that configuration, the other one. And after doing thousands of measurements on psi, you basically can recover the probability distribution of configurations. So you know with which probability these configurations occur. And now you can use this probability distribution of configurations to actually calculate interesting correlation functions. So now out of this information, you can start to calculate physical quantities. For example, like this one, you could ask the question, well, how likely is it if I have one atom here and two atoms over here to have a hole in between? Or what's the environment surrounding a hole? If I have a hole here, how does the environment surrounding the hole look like? Okay, so these are all questions that now become accessible to you. And these are really important questions, as we'll see, asking these so-called non-local correlation questions, how the system behaves, will give us a lot of insight into the many-body quantum state that the system has. All right, let me show you a few pictures, how that this really works. So here I schematically sketched the optical lattice. So first of all, we have a lattice created by one beam here, another one coming from the lower half, which makes these planes of standing wave here, these two-dimensional planes in which the atoms are trapped. And then we can have lattices in the X and Y direction created by these beams that create, for example, a square lattice in the plane. And then if we only load atoms into one of the planes, they will be loaded into this lattice, and we realize the psi that we want to study. And then if we want to observe the system, we basically do the following. We shine near resonant light onto the atoms, onto this trapped gas, onto the state psi. And when we start to see fluorescence photons being scattered from the atoms in this plane, that's exactly when this measurement is done. That's when the quantum state actually collapses and you get to see one configuration of the atoms. So here's a picture. So this is how this looks like in reality. This is a picture actually of a thermal cloud now, but you can actually see each bright spot that you can see here. That's like an individual atom that is trapped in this crystal of light, which you cannot see, but you can just see the atoms trapped. If you look a bit careful in the zoomed in picture, you see there's really a regular grid onto which these atoms are trapped, which you can actually see now when you see the presence of each individual atom. And you can see actually the signal to noise is very, very good. We scatter a few thousand photons to get a signal like this from the atom. And then you can basically extremely well see the atom in this lattice. We'll also talk a little bit later about manipulation possibilities. So if you can see individual atoms, then you have the optical resolution to also address individual atoms, because what you could do is the following. If you can send a laser beam through the reverse direction through the objective, then it will be focused down onto a single lattice site. Because if you have the resolution to see a site with this objective, you also have the resolution to focus a laser beam in the reverse direction onto a single atom. And then we can control the spin states of these individual atoms in these lattices, for example. And just to show this, I show you here a nice example picture where these white dots here, these mark the position of the optical lattice sites. The fluorescent atoms you can see here recorded after we, for example, moved them around in the system or positioned them in a special arrangement pattern. So here's like a square of 6 by 6 atoms. Here's a star pattern. And here, of course, as quantum physicists, we like to make a psi out of 26 individual atoms trapped on this optical lattice. Okay. Okay, I see there are a few questions. Let me try to go down this question. For the measurement, there was a question, each state shall be observed with some probability. That was correct. Yes, that answer we had. It's a question, after multiple measurements, you have a density matrix with probability of each configuration as diagonal element. Is it appropriate to write it as a coherent superposition? Well, I just took the example of the coherent superposition as just a simplified example of what's going on. So in principle, of course, we always have a density matrix for the entire many-body system. We probably never have a truly pure state there. But again, after one measurement, that's important that you ask this. After measurement, you don't have psi anymore. After you do a measurement, you have this state, for example, if it collapses onto that state. And this state is not psi anymore. So if you want to basically redo the experiment, you first have to recreate psi. And that means for us, we have to go through the whole laser cooling and creation of our BEC or Fermi gas, for example, loaded into the lattice. And then we recreate psi, and then we make another measurement onto the system. So that's important. The measurement is absolutely destructive for the quantum state. So once you made a measurement, it has to be destructive because you're gaining maximal information on the system. It's a strong measurement, so to say, and you have to destroy the initial quantum state. All right, let's go back to the picture. Yes, let me just finish off and say that you can be actually very flexible in what kind of potentials you generate with the light fields. I showed you how you can interfere laser beams and how you can realize optical lattices, but you can also just project light fields onto the atoms. So for example, this is a so-called digital mirror device. It's probably something that you have in your projector in your university or school also, which is when you project from this projector an image onto the screen, you basically have small micro mirrors in this digital mirror device, which you can tilt on and off with a voltage that you apply to these micro mirrors. And that allows you basically to project arbitrary light patterns onto a screen, onto your projection screen. And we can use the same method to project arbitrary light patterns onto the atoms. So we can, for example, shine a Gaussian laser beam onto this digital mirror device, and out we get a light field, for example, that is this line of light, or that is this more exotic lattice configuration. Or if you want a square box potential, and we can realize a square box potential. Or if you want to study the quantum transport between two reservoirs, you can make two boxes connected by a very, very thin wire of light. And you can fill up this box here with atoms, which can then flow very slowly from this reservoir to this reservoir here. And you can study, for example, the conductance of this light wire under the presence of disorder, magnetic field, or whatever it's interesting that you want to study. And this is something, for example, Tilman Esslinger has been doing extremely successful in his group. All right, a good moment to pause for a second. Are there any questions, any more questions that you would like to ask so far?
There is one question in the chat box.
Yes.
How stable are the individual components of psi under repeated measurements?
Yeah, so that's actually quite stable. So so if we don't heat the atoms too much, if we have a detection process which also cools them during detection, then once you collapse and you see that configuration and you measure again, you're going to see exactly the same configuration again. Now, what could make it unstable? What could make it unstable would be a bad vacuum. If you have a bad vacuum, for example, there could be a collision with the background gas that just kicks out one of the particles. And then if you take a photo, of course, that atom would be missing and you would see that atom being lost. That would be one process, how you can lose an atom basically in this detection process. And this is something we have to take a lot of care about.
Can I ask one question that on the repeated measurements, do you see quantum Zeno effect in this situation?
Quantum Zeno, yeah, we didn't do that. So here you really make a strong measurement, and we didn't look. We didn't do a repeated strong measurement to let's say inhibit a time evolution of the system. So, but that's something that other people have done. So you can also use that to look at quantum Zeno effects of a many body system. Yeah, so people have done that.
Thank you.
Okay, any more questions so far? Comments? How are we doing? Too fast, too slow? You give me a hint, right? So you just type in the chat box or you speak up how we're doing with the speed, so I can adjust a bit the speed of the talk also. Okay, so let's continue. Let's look at the first physics experiment that we can do here. And that would be a very simple experiment where we just place a single atom on a lattice side in the 1D configuration, and you want to see what's going on now. If you let this atom go now, you let it evolve in this one-dimensional lattice, what's going to happen with it? Yeah? So I told you the atom can tunnel from one side to the next. So what will happen, of course, is if you look at these individual atoms, they will spread out. Yeah? And then when we do a measurement, we'll find their position. And what's, of course, wrong in this animation is that we never know which atom is the fastest atom or which atom is leading. We have a wave function that is evolving, giving rise to, in the end, to a probability distribution of particles, arriving at some point. But in a single measurement, we can never say which is the fastest atom or the slowest atom. But so here's our experiment. So here's the 2D lattice, x direction, y direction. We make the lattice in the y direction extremely deep by making the laser in this y direction very, very intense. So the atoms can only tunnel in the x direction, okay? So where the barrier is low. And the y direction, the barrier is just so high that they cannot move along the y direction. We start out with a single atom here and now on this single site, and now we let it evolve and do a measurement, okay? So what are we going to see? Well, here are single shots, for example, of what happens after a certain evolution time. You see, for example, this picture. So you see actually this particle here has moved quite far. There are a few which haven't moved at all. And so this one was obviously the winner of this race, of this quantum race that we did. And then quantum races, of course, particles also move backward and forward. So not like in a horse race in one direction, they can move in both directions. So of course, here, this is just a single snapshot. And if we do it again, experiment thousands of times, we can then recover the probability distribution of the particles after a certain evolution time. And this is now what we have here is the histogram of occurrences of finding the particle at a certain position on the lattice. And the bar plot, that's the experimental data. And the red line, that's just a calculation from Schrödinger equation, just simulating this so-called quantum walk, continuous time quantum walk in this system with the Schrödinger equation. And you can see they agree actually very, very nicely with each other. We can do this even for longer time evolutions. And you can see that this probability distribution that you get here from this quantum walk really beautifully matches what we see in the experiment. So we really have this fully coherent tunneling motion of the particle on this lattice over these 20, 30 lattice sites, different separations. So I want to say this is quite different from what a particle in free space does. So how does a particle in free space spread? If you take a localized particle in free space, not in a lattice, let's say here, and you let it now evolve in time, what's going to happen? How does the probability distribution look like? And what would you say? So if you have just a localized particle and you just let it evolve in free space, what's going to happen? I'm sure you all calculated this once in your quantum mechanics course. How does this look like? Any guesses? So is it clear what I mean? So let me try to make a sketch here. Let me see if I can. Do we have actually, sorry. Back here. Yes, this wave function spreads evenly in, yes, very right. Broadening of the wave packet, excellent. Yes, this is what happens. So you just, actually, can I draw on the screen? Let me just see. Did you enable screen drawing, or can I not draw on the screen? Because I don't see the button to draw on the screen. I don't think I can draw on the screen. Anyway, so yes, what you're answering is completely correct. So you have this broadening of the wave packet, where basically in free space, if you have a Gaussian wave packet, remember the only thing that happens, it just broadens, spreads out in space. Yeah. On a lattice, you see, however, the probability distribution is very different. You start with a localized particle, and what comes out in the probability distribution is not a Gaussian, but this very strange probability distribution where you have a high probability of seeing very fast particles in the system and a lot of interference structure in between. And that's very characteristic for this motion or this quantum walk, for the so-called quantum walk on this lattice. Because it's like every time you tunnel, you can hop from one side to the neighboring sides and the neighboring sides, but you can also hop back. And when you hop back, there will also be a probability of interference of the waves of going forward and backward. And this probability, this interference of amplitudes, gives rise to this very strange kind of probability distribution that you can actually readily calculate, for example, yourself, if you just look at the tunneling of the atoms on this lattice. All right, very good. So that's what happens.
There is one question.
Yes.
From Shubhashish Dattagupta. Is
Yes.
there any experiment on Bloch oscillations and linear Stark later on such systems?
Oh yes, absolutely. So Bloch oscillations, beautiful experiments. I maybe should have included them. Indeed. So what are these Bloch oscillations? So what they are is basically when you tilt the lattice potential, when you apply a force. Okay, let's imagine you apply a gradient potential. So you apply a force to your particle. So now in free space, the particle would, of course, just basically roll down the hill and accelerate. But in this quantum particle, what actually happens is that the wave function spreads out and comes back together again, spreads out and comes back together again. So this is the so-called famous Bloch oscillations that occur in the system. And actually here I give you some references where you can look up those Bloch oscillations and see those dynamical evolutions in a tilted optical lattice potential. That's where these Bloch oscillations actually occur. Okay, any more questions, comments? Okay.
But at this moment, none.
Okay, all right. Okay, so let me move on from this single particle physics to spin physics to show you how in these systems you get a spin-spin interactions between atoms or electrons in a solid just based on this Hubbard model. Okay, so this is a bit surprising, and this was surprising. If it feels surprising, it wasn't only surprising to you, but in the 50s, in the last century, people, were really scratching their head why there is this spin-spin interaction between, for example, electrons that are located on separated lattice sites which are not connected to each other. And the reason for that is the phenomena of super exchange interactions that I want to explain to you and show you how from this simple Hubbard model we actually get spin-spin interactions in the system. So let me start with the Hamiltonian, describing in a bit more formal terms what I talked about so far. So we have the tunnel motion from the particle from one side to the next. So this I and J labels the lattice sides. So let's say this is the destruction operator for destroying a particle on side J. This is the creation operator for creating a particle on side I. And we hop from side J to I with a tunnel coupling strength. Now I write it as J. Sometimes I write it as J, sometimes as T. So you have to make sense of what I'm meaning actually, but I hope it will be clear in the slides. So you hop with the strength given by this amplitude J, and the negative sign just means that you can lower your energy by delocalizing the particles. So kinetic energy will be lowered if you delocalize the particle. And this process basically just corresponds to hopping from one side to the neighboring side. You destroy the particle on side J, you recreate it on the side I, which is adjacent to J. This is what's denoted by these brackets here. And then you have the sum over all those hopping possibilities that occur in the system. Then you have an interaction term that describes these coherent collisional interactions that I talked about. So when two particles come together, you have an interaction energy of U. This is what this term does for bosons. This just counts the number of bosons on site I. So if this is 2 times 1 divided by 2 gives us exactly an energy cost of U. So what I want to show you now in the next few slides, how from this model here, in the regime of strong interactions, so in the regime of U being much larger than the kinetic energy J, we actually end up with something like this, which is just a spin-spin interaction term, where now you have the spins on site I interacting with the spins on site J. So let's consider a 2-component gas of atoms in a double well in this very simple example. So let's say we have a spin up particle, red, and a spin down particle, blue here. And we have this Hamiltonian, and we have these two types of atoms in there, and we are in the regime of strong interactions, so strong repulsive interactions. So and now there's tunneling. Well, you could say, well, then this atom is going to move over here. But now I'm going to tell you, well, this is not going to happen. Why is this not going to happen? Why is this forbidden? For the situations I showed. Why is this forbidden that this particle, this red one, just hops over here onto the neighboring side? Why would that be forbidden? You can also just unmute yourself and just talk, and don't have to enable the video camera, just shout, and there's no problem if it's wrong or right. We're just trying to get a bit more interactive, so I get a feeling for how you're getting along with the lecture.
Are they fermions?
No, they're not. Well, fermions wouldn't matter here as well, because they're 2 different spins, right? So they're distinguishable particles, so there's no Pauli blocking that forbids this particle hopping over here. But that's a good answer already, yes. But that's not the right answer.
I think because of strong interaction.
Strong interaction.
Yes, very good. So it's the strong interactions, of course, which forbid you. If the energy cost of bringing 2 particles together is much larger than J, then of course you cannot hop over here simply because you don't have that energy, right? I mean, there's an energy penalty to go over here. And if the kinetic energy is smaller than this repulsive, for example, interaction energy, then you just cannot over here because you don't have that kinetic energy, enough energy to promote the atoms to double occupancy here. Okay, so you cannot hop there, you cannot stay there. But in quantum mechanics, you can do it in a virtual process, in a so-called virtual process. And this is what we would call a second order. We can derive that in second order perturbation theory. So let's start out with a Hamiltonian where U is the largest term, and we take J as the perturbation term in quantum mechanics. And then we calculate the processes that can happen in second order perturbation theory with this kinetic energy hopping term. So what can happen is the following. The particle can hop virtually to that site, but then it cannot stay there because that would cost an energy U, and it doesn't have that energy U, so it has to go back. So it can go back to the original site, so we're back to the original configuration. So this is one outcome of the second order perturbation energy process. Or actually what can also happen, that the blue atom goes back over here. So the blue atom now goes back, and then we're also in a configuration which is energy, which has exactly the same energy as the initial state. So you see this final state and this final state has exactly the same energy as this initial state here. So they're both processes that are resonant, that fully conserve energy, and are both possible in second order perturbation theory. Now, what's the amplitude of such a process? Well, we just have to calculate the matrix, twice the matrix element for hopping once here, hopping back. That gives us a J squared term. So this is the 2 times hopping process, hopping back, forward and backward. This gives a J squared term. And then remember, in second order perturbation theory, in the denominator, you basically have the intermediate state energy that you occupy only virtually. And that intermediate state energy here is this state, and this is energy U, as we said. So then you have in the denominator a U. So the amplitude for such a process is J squared over U, right? Okay, so now there are 2 processes that can happen. You can go in second order perturbation theory back to the identity, or you have exchanged the position of your 2 atoms, which will be given by this exchange operator. And the total possibility in the system then is just the sum of those 2 operations. And they each occur with an amplitude of J squared over U. This is the second order perturbation theory amplitude. And this other factor of 2 simply comes from the fact that the right atom could also have hopped to the left atom in this process. So you have twice this process occurring. So this is the effective Hamiltonian that you can write down for this system in the regime of very strong interactions that emerges in second order perturbation theory with this virtual hopping process that I described to you. Now let's look at the eigenstates. What are the eigenstates of this operator? Let's try to find the eigenstates of this operator. Well, the eigenstates of this operator, we have to find those. We have to see what basically happens to the eigenstates. What are the eigenstates of this exchange operator? And the eigenstates of this exchange operator for our 2 spins would be the symmetric and antisymmetric combinations of the spins on the 2 lattice sides, up, down, minus, down, up. If you exchange that, gives us minus the original state, or exchange operator acting on up, down, plus down, up. The symmetric state in the double well would give us plus the original state, right? And the identity, of course, always gives us the original state back again. So now we can write down the eigenstates and we can characterize their energies. These are the singlet and triplet states. This is the singlet state, the antisymmetric state, and the triplet spin state in the system. And we can also say that now for these ferromagnetic interactions, for the bosons that we considered, these triplet energies is going to be lower in energy than the singlet energy. And this is going to be then the ground state of the system, and the singlet state is going to be the excited state. So this would be the case for bosons. If you do the same calculation for fermions, you have to keep in mind that when you exchange 2 particles, you also reverse the sign of the 2 particles, right? So there's the exchange -1 factor from exchange symmetry for fermions, which changes the sign of this Hamiltonian. So for fermions, you do exactly the same calculation than for bosons. The only thing that differs is that now you basically, instead of a minus J exchange, you get a plus J exchange here. Okay, so then what that means for the spectrum is that the triplet state is now the highest energy state and the singlet state is the lowest energy state. So now we've learned an important lesson that basically, well, let me do one more step now and convert this into a spin Hamiltonian. So if this operator that you see here is just a projector into the triplet subspace of your system, then you can rewrite this as this triplet operator as a sum of your individual spins on the left and right lattice side. And if you basically square that, you get this SLSR term. And you know that the sum of the 2 spins that you get for 2 spin 1/2, the total spin that you get is S times S plus 1, with S being the total spin, either being a 0 or 1, the singlet or triplet combinations. And that means now that your total Hamiltonian can be written as this exchange energy scale, this 2J squared over U term, times the spin operator for the particle on the left side times the spin operator for the particle on the right-hand side. So this is actually now quite remarkable. We started out, let me remind you, we started out with this Hubbard Hamiltonian. The only assumption we made is that we're in the regime of strong interactions. And from purely local interactions, this is just purely local interactions that occur just when the particles are on the same side, we ended up, because of these second order hopping processes, with a Hamiltonian which now describes spin-spin interactions on neighboring lattice sides. This is the spin of the particle on the left side and the spin of the particle on the right side. And this is a so-called Heisenberg Hamiltonian that emerges in the strong coupling limit from the Hubbard Hamiltonian. And again, for bosons, you would have this minus sign here with J exchange being positive, and then you would have a system which favors parallel alignment of the spin. So you can minimize this energy by aligning the spin. So you have a ferromagnetic interaction. And for fermions, actually this J exchange is negative. So now you actually minimize energy when you anti-align the particles, which is why for fermions, these fermions want to align antiferromagnetically, whereas bosons, they want to align ferromagnetically. That's a fundamental difference in these systems. All right, this was a bit complicated, maybe, a bit maths. How are we doing? Questions on that? Any questions for that?
Yes, there are a few questions.
Yes.
One question from Sadiq. Is not there a distinction between a stepwise hopping and a single atom and the exchange in terms of probability?
Well, yes. So the single particle hopping is actually suppressed. We'll see that in a second in the data. So this single particle hopping would simply, if you think of it as a two-level system of this state coupled, this initial state coupled to that initial state, and that would be just off resonant. So it would be like if you're more familiar with a two-level system, it would basically be a driven two-level system, but very detuned, very large detuning, right? Because the U creates an energy difference, and this large detuning would mean that this Rabi oscillations would be very, very low amplitude. So that's highly suppressed. Okay, was there another question?
Yes, there is another question from Anushree. Is the exchange operator something similar to a parity operator?
Parity is a bit different. Parity operator basically gives us the wave function, the spatial symmetry of the wave function. Here, the exchange operator just exchanges the position of the two particles.
Another question from Kumar Gupta. Can there be a situation where the particles would have to be considered as identical particles, so the Pauli principle would play a role?
Yes, absolutely. So let's just do the Gedanken experiment for ourselves. Let's imagine I don't have a red and blue particle. Let's say we're dealing with fermions. Okay, let's do this same calculation for fermions, where now just have a spin up on the left side and a spin up on the right side. What would you say now? What happens to the whole physics I described to you? Can this process happen or not? So what would you say? If we have, instead of the blue ball, we put a red ball here as well. So now we do the same line of argument. Can that happen or can it not happen? And if yes, why? And if not, why not? Cannot hop, probably, from Kumar. Yeah, but I want to know why. If it cannot hop, tell me also why it cannot hop. Or if it can hop, tell me why it can hop. Yes, so Noah says U becomes infinite effectively. Why does U effectively become infinite? Yes, Pauli exclusion principle is the right answer, of course, because we cannot put two fermions in the same orbital. And if there would be just one orbital here, we cannot hop over here. And Pauli exclusion principle forbids us to do that. So actually, in the case of two identical fermions, this whole thing just vanishes. This whole process here vanishes. What about bosons? If I have two bosons, if let's say this would be a red boson and a red boson over here, can this process happen or not? What did you say? Kumar says yes. Somebody else? Why can it happen? What would you say? Why can this process happen for boson? Well, let me answer. So yes, it can happen for bosons. Simply, of course, yes, it does not violate. There's no Pauli principle. You can put two bosons on the same lattice side. So this process is perfectly valid for two bosons. Yeah? So you already have learned an important lesson here of what works and what not. Okay, so now that we understood this, let's do an experiment. Let's learn a bit more about this Heisenberg Hamiltonian. So you see in the limit of strong interactions from the Hubbard Hamiltonian, we get the Heisenberg Hamiltonian. And let me actually rewrite this spin operator, which is just Sx, Sy, Sz here. A little bit different. So if I would just multiply this out, I would get Sxi times Sxj plus Syi times Syj plus Szi plus Szj. And then you might have heard of these ladder operators, which are just linear combinations of Sx plus Isy and Sx minus Isy. And we can rewrite this first part, the xy part of this spin-spin interaction, in the following term: S plus times S minus plus S minus times S plus. So what does this operator do? This S minus and S plus operators, these are so-called spin flip operators. The S plus operator takes a spin down on side I and converts it into a spin up. The S minus operator takes a spin up on side I and converts it into a spin down. So it basically flips the spin. So you actually see that this XX and YY part of the Hamiltonian that we had here, and then there's the ZZ part, which we have to talk about in a second, actually. This XX and YY part of the Hamiltonian there give rise to this S plus S minus plus S minus S plus. If I compare that actually to my A dagger A term, it has a very similar structure that you saw in the Fermi-Hubbard model. And therefore, you know, here you also have something with plus and something destroyed. And so it looks kind of similar. And this similarity has a more profound underpinning, actually, because this, as we'll see, actually, this S plus minus term that we have in the Hamiltonian is very much like a kinetic energy term, very much like this A dagger A term that we had for a single particle on the lattice. But now we're talking about spins in a spin chain, okay, or these two spins on this double well. Okay, so let's do a very simple experiment. Let me start out with this spin up, spin down configuration. I have a spin up on the left side, a spin down on the right side. We just derived this Hamiltonian, and we know that this is not an eigenstate of the Hamiltonian because it would have to be a state which is symmetric or antisymmetric under exchange symmetry. And this one is not. Obviously, if you exchange the particles, you don't come back in the original state. So it's going to show some dynamical evolution. Well, what is the dynamical evolution it's going to show? Well, let's just act with this Hamiltonian onto this state. So what about this last term? What does this last term give us if we act onto this state? What would you say? What does this Hamiltonian here give when I act onto this initial state? So the SZ operator of the right well, the SZ operator on the left well, what would it give me? Just unmute yourself and shout. And there's no wrong answer. We're just trying to try to understand the physics together. J fourth, yes. A state remains unchanged, and J fourth, that's completely right, because for each one SZ, you get 1/2. Another one SZ 1/2 gives you 1/4. If they are anti-aligned, as shown here, you get minus 1/4. So it would give you plus J exchange quarter for the energy. So it just gives you an energy offset. What about this term here? What does this do? What does this term actually do? This is plus minus operator. Let me act with this first operator here on this state. Well, that's going to give me nothing because I'm already S minus here, that I cannot lower the spin anymore here. So that's going to happen. Nothing's going to happen. But what about this state here? This is plus S minus. Well, S plus S minus, remember that one is going to flip the downspin into an upspin. And this operator S minus is going to flip the upspin into a downspin. So eventually you got from this configuration to that configuration here. And once you're in this configuration, well, then this other operator acts and can flip you back. So now you see the whole dynamics is encoded in this Hamiltonian, which basically just means that we're going to flip-flop between those two configurations. If you start with the up-down configuration, you're going to flip-flop back and forth between those configurations. That's the dynamical evolution that you expect, simply because of these virtual hopping processes we had in the ladder. Okay, let me show you that this really works. So I show you some data that we did actually this experiment, and we looked at how does the population in the two wells, the population difference in the two wells look like over time for different ratios of kinetic to interaction energy. So this would be larger kinetic energy. This would be lower kinetic energy. So the ratio J over U is small. So this is the strong interaction limit where we expect the Heisenberg dynamics to emerge. So actually, the first thing you see, if you don't look at the density, if the density actually always stays flat, there's no population difference that builds up in the dynamics because you start with one atom left, one atom right. On average, the density just stays constant, and then there's no population difference. But if you now look at the spin imbalance, the spin difference in the two sites, how that evolves as a function of time, you actually see this very complicated dynamics. But you see actually in the regime of just very strong interaction, there's just one kind of sinusoidal oscillation that emerges, and that's just the flip-flop interaction I talked about. That is precisely this flip-flop interaction, the spin-spin Heisenberg interaction that I talked about. Yeah? The reason why it's damped a bit here is simply because we did this experiment at the time in many, many double wells, and each of these double wells had slightly different flip-flop rates, so they just dephase relative to each other, so you don't see them so nicely for a long time. So for a perfect scenario, you would see this very continuously going on. So what you also see is as we increase kinetic energy in the system, if we go lower here, then you see actually more and more this small wiggles coming up. or here even more complex dynamics. What do you think are these small wiggles? Where do these small wiggles actually come from in this graph B? What process, what physical process do they describe? No vibration. There's no vibration here. Also no quantum fluctuations. It's also a good answer. Could be quantum. The wiggles always could be quantum fluctuations, not quantum fluctuations. No lattice defects. We just have a double well. We just have a double well, and we just have the Hubbard model that I showed to you. No long-range ordering, just double wells. So what's happening? Remember what I'm doing here. I am decreasing U. I'm making, you're getting a pairing of atoms at the side. You're getting slower to atoms. What's happening, of course, if we decrease U, we are decreasing the energy penalty of that atom, single atom, just to hop to the neighboring site in a first order direct hopping process. So actually what you're seeing here is the off-resonant first order hopping process. So you're seeing this Rabi oscillation that is very detuned and very low amplitude because of the large detuning that is now emerging. And now if you make the interactions actually even weaker, now you actually do have enough energy, kinetic energy, to hop onto the neighboring site. So now the first order hopping happens, the second order hopping happens, and you have these two time scales that come in now and give rise to this complicated, more complicated looking signal, which is just really these two energy scales you have in the problem. The single particle tunneling, which is now becoming more and more allowed, and the exchange process, which is also still allowed, that we just discussed. So you have these two possibilities that occur in the system. Okay, so now let's move on. We now understand what's happening in the double well. We see how this Heisenberg model emerges from the Hubbard model, how you can actually get quantum magnetism from just having strong interactions and exchange symmetry. Those are the only two ingredients that you have to get this Heisenberg Hamiltonians. And remember, in the case of two-component bosons, we get a ferromagnetic Heisenberg model. In the case of two-component fermions, we get an antiferromagnetic Heisenberg model. Okay, so now that we know what happens on the double well level, let's actually go now to a chain of spins and see what happens there. And so now we start out, for example, with the bosonic Hubbard model. So we have a ferromagnetic chain in the regime of strong interactions. And now we basically flip one spin here in the middle. Okay. So we flip one spin in the middle here, and now, just as we did in the double well, now what's going to happen? We expect, of course, this exchange where this spin can hop to this side and this spin up hops to that side, so they just exchange their position. And that's this S plus S minus term. And remember, it's now like the A dagger A term that we had in the kinetic energy, which now allows this single spin to propagate now through this chain. Okay. So we do this experiment. So we take an array of one-dimensional systems created in our quantum gas microscope. We shine a line of light onto those atoms to rotate the spin just in one position. And then we start the time evolution of the system, and then we measure where is this spin down at a little bit time later in the system. And as I showed you, we can now really nicely understand what's happening, because we can rewrite the Heisenberg Hamiltonian, that is the effective Hamiltonian for the spin chain in the regime of strong interactions, as this S plus S minus term plus the SZ term. The SZ term is not going to change irrespective where that position of the single spin is. You know, if the single spin is here or over here or over here or over here, this part, as you can just verify for yourself, is just going to give an energy offset, and it just, not going to play a role in the dynamics. What is going to play a role in the dynamics is this part here, this S plus S minus term. And if I compare it again to the single particle tunneling, it has exactly the same structure as the single particle tunneling on a lattice. So in a single particle on a lattice, we just learned what we get is this quantum walk with this very strange probability distribution. Now, if you have a single flipped spin in a ferromagnetic chain as shown here, you actually expect exactly the same dynamics, because this S plus S minus does exactly the same thing as the A dagger A. The energy scale is now not the Baire hopping, but this exchange hopping process that comes from this virtual hopping processes in second order. But the physics actually is the same. So you don't expect anything different, and lo and behold, you precisely see that. So here's the probability of that spin, of finding that spin. Initially at time 0, we find it localized to this initial site, and then we increase time in the system, and we look at the probability distribution. And we, of course, again, have to repeat the experiment many, many times. And then we find the probability distribution of the particle. And the red line is basically this probability distribution we can just calculate, again, from this S plus S minus term from the Schrödinger equation. And you see it's exactly the same probability distribution that we had for the single particle tunneling case. Okay, so the physics is exactly the same. Now I want to go a bit step further and show you where things get more interesting when we have to worry about this Xzz term, which did not play a role so far because it was just for the single impurity a global offset. Let's now look what happens if you have when this term can play a role. And this is actually very, very a fundamental discovery from Hans Bethe, where he developed the so-called beta ansatz that allows us to give us exact solutions for such spin chains, for example, for such integrable systems. And he actually understood, he looked more at the problem, when does this Xzz term become important? And so we now look at a more generalized version of this Heisenberg Hamiltonian, where you have this xy term, the S plus S minus term, this is this one here, where this could be slightly different than the Xzz term. So the model I showed you so far, the Heisenberg point, was the case where these terms have the same strength, where J exchange equals delta. But in principle, you can study such anisotropic models, as they are called, and these are called Xxz models. So this XX is the kinetic energy part, and the Z describes the separate energy scale we have for the Xzz interaction part. Now, the question is, of course, when does this play a role? And this will play a role when I, for example, have two spins that are aligned to each other, because now you can see when these two spins are neighboring each other, you will have an energy lowering. If they're not neighbored to each other, they will have an energy penalty. Okay, so these spins really, because we have ferromagnetic interactions, remember, they really want to stay aligned and they want to stick together. So there's like an attractive energy now acting between those two spins that wants to keep them aligned and not want to break them up so they tunnel independently. And this was actually found by Bethe, that this is a more general solution for this. He found that there are these so-called L strings, where you can not only have two atoms bound together, but 3 or 4 atoms bound together in this ferromagnetic interactions. All right, so let's look at that. Let's look at what happens to such two spins that are initially aligned and form a bound state. We call this the bound magnon, that cannot separate because of this Xzz interaction energy that will now propagate together through the system. So there are two possibilities what can happen. You either have this bound state, so the two spins move together through the chain, or, well, if there's a little enough kinetic energy compared to the binding energy, so if this first term, the XX term, is large enough, then the kinetic energy might be large enough compared to the interaction energy term delta to break up those two spins, and they could propagate independently. So now it's a question again of how strong the binding energy is relative to kinetic energy, how strong the upper process is relative to the lower process. So to describe that, I calculated the evolution for you in this plot. So I'm plotting here now first for the non-interacting case. Non-interacting meaning the Sz term here, this term is 0. And we only have this kinetic energy term here. Okay, that would be the non-interacting case. And now we look at the following situation. Go quick again. Where we start out with the two spins, aligned spins neighboring each other. So this is the position of spin 1. I coordinate here x1. This is the position of the spin 2, x2. And at time t equals 0, they are right next to each other. And what I want to know, how does this probability distribution of finding spin down at position 1 and the other spin 2 down at position x2, how does this evolve over time? Now, if you have no interactions between those two spins. There's no binding, and they can basically propagate independently. And you actually even see some slight anti-bunching here in the system. So whenever the second particle shows up at a large positive distance, the first particle shows up at a large negative distance in the system. So now let's actually have a look what happens if you are at the bound state case, where now you have a attractive binding between the particles. And now you evolve the system, and now you see you also have a little bit of these blobs on the diagonal, but not on this side here. But now you have this new phenomena occurring here right on the diagonal, which means that those two spins always hop together through the lattice. So with higher and higher probability, those two spins now really form a new entity, a new particle, a new quasi-particle, as we call it, this bound magnon that now moves together through the lattice. And we can increase in the calculation, we can make this interaction energy even larger. And then we can see we even less and less have this blob separating, the spin separating, and we have them even more and more sticking together because the attractive interaction energy becomes larger and larger, and they just want to stick more and more together compared to the kinetic energy. Here's the experiment where we did exactly that experiment. So we flipped not only one spin in this spin chain, but we flipped two spins, exactly with the same method I showed in the animation before. And then we have two neighboring spins right next to each other, and then you let them evolve, and you see that indeed on the diagonal you have these two spins hopping together, these magnons propagating together in excellent agreement with what we expect for theory for this Heisenberg case where delta is 1, where we have the exactly same interaction strength between kinetic energy and interaction energy. Yeah, so one final thing, maybe there's just also a different propagation speed for the single spins. They move faster than these bound objects, these new kind of solitons, magnetic solitons in the system. And Bethe was able to calculate the difference in propagation velocities. He showed that the ratio of free magnon propagation velocity to bound magnon propagation velocity is just 2 times this binding energy. And in our case, remember, delta is 1 in the Heisenberg points, so we expect this ratio to be exactly 2. And the experiment we found 2.3 with an error of 3. So again, in very, very good agreement with the prediction from Bethe. All right, so that's all I wanted to actually say today on the quantum dynamics of individual spins. So I want to recap what I talked about today. In the first lecture, I showed you how we create these optical lattices, how we can load atoms into these optical lattices, how we have the Hubbard model describing the tunneling and on-site interaction in these systems, a very, very simple model. And I also showed you how in the regime of strong interactions, strong repulsive interactions, and every site being occupied by a spin, how we get this emergent Heisenberg Hamiltonian with describing neighboring spin-spin interactions from this Hubbard Hamiltonian. So again, the ingredients are strong interactions, strong repulsive interactions, and exchange symmetry, which give you from the Hubbard model the Heisenberg Hamiltonian. And then we discussed a few examples of the dynamics of this spin Hamiltonian. In the case of just a single spin impurity, we saw that that's just like a single particle. And then we had, in the case of the ferromagnetic Heisenberg chain, we had these bound magnons where you have new quasi-particles that can stick together these elementary spins and form new bound states that then propagate together through the lattice, because of this interaction part, this SZ part. So again, how you should spin Hamiltonian, let me just recap again, how you always should think about this Xxz Hamiltonian. You can always rewrite it as this kinetic energy part plus an interaction energy part. And it's always the physics in the system is characterized by the ratio of kinetic energy to interaction energy. That tells you what you're actually going to see. All right, I think that's all I wanted to tell you today. Any questions, comments?
There are a few questions.
Yes.
Nalkanti Giri asks, how probability distribution related to Bessel function?
For the single particle, actually, it turns out you can drive an analytic solution. It's exactly the Bessel function of the first kind. So this interference pattern on the quantum walk that you get, and I didn't show you the calculation, but you can show that there's an analytic solution for that, just for the single particle. And for the single particle, this is just this Bessel function of the first kind that describes this probability distribution.
Question from S. Gupta. when you measure the probability distribution experimentally, is it true that the square of the individual coefficients add up to 1, or to what approximation that happens?
Yes, well, it has to add up to 1. There are, of course, experimental errors that are there, but we have to conserve probability. So all events have to occur at some time, or they have to sum up to 1, the probabilities of the individual events. Yes. So indeed, they do sum up to 1. Of course, up to experimental imperfections that we can have in the system, right? I might lose an atom in the detection process because my detector is not perfect. But that's then something I have to take into account.
The next question is from Arnav Sarkar. Is this probability plot same for infinite and finite chain?
Sorry, so is this probability?
Same for infinite and the finite chain.
T meaning temperature or meaning time?
I mean, the probability distribution, if you consider an infinite system, how does it compare with the finite system?
I see. Well, of course, for a finite chain, at some point, you would have reflections from the boundary, right? I mean, if we would have this chain, if we would have, let me see. If we would have really the chain terminated here and here, then once, of course, this particle reaches these boundaries, it will be reflected back and the probability distribution will look different then. So I didn't take this into account. So I always assume for now, this is an infinite chain.
So the next question from Sourav, what happens if the experiment is done in a ring lattice of atoms?
Very good question. Well, then, of course, those waves, you will have this wave propagating to the right and to the left, and it will come back to itself, and there will be some more complex interference structure that you get then. But in principle, you just keep propagating in those two directions, and when those two waves meet on a ring, then of course you will get some more complicated interference patterns. So it will change the probability distribution that you get then. But initially, it will look exactly the same on the ring as on the infinite 1D linear chain if the waves don't meet each other yet.
Anshuman Nayak asks the question, how different will be the dynamics of spin chain if the exchange interaction is antisymmetric?
I don't know if what you mean by antisymmetric. You mean if there's you mean in the Xxz model, if the Z term is, if this term is different than this term here, well, then as I showed you, then these bound states here will give rise to a different dynamics in the system. So you want something different. If you want a minus sign, well, one has to see if that it can even be physically realized. You have to have a mission operator, so one has to, of course, always check whether whether the right term that you write down is even a valid physical hopping term. So I think I cannot answer in general. It really depends on what kind of kinetic energy term you are considering, how you would want to modify this part.
May I ask a question, Bimalendu?
Sure.
Yes.
Actually, if you include the effects of bath, let's say your system interacts with the bath variables, then what is the immediate effect on what are the timescales within which you have to perform your experiments?
Well, what would happen immediately, you would lose this interference structure. Of course, again, now there's a question of the bath system coupling will, of course, determine how long you will be able to see the coherent propagation of the spin, which is what we talked about here, or you have coupling to the bath, which would decohere this coherent structure. So it would wash out your interference fringes. And in our case, because as we said in the beginning, this black body radiation is very well decoupled from the system. It takes can take minutes or hours to thermalize the system through black body radiation. We are very well decoupled, so we basically are not coupled to a reservoir.
Thank you.
Yeah, that's a nice thing that you can study this coherent propagation of the system because the system is so well isolated from the environment.
So can I ask one question that I have noticed that in the lattice you have prepared the atoms in the highest magnetic sublevel. Is there any reason for that?
In the lattice? No, no, you could do the same thing. It's completely, it's not, well, no, this would be it's not the highest state. So all of them aligned would be the lowest state, and then we flip one spin. Okay, so we align them all. So it doesn't matter in this Heisenberg model, it doesn't matter whether spins are aligned in the X, Y, or Z or any other direction, because this model is isotropic in space, right? It just counts that the particles are aligned, but which direction they are aligned in is completely free.
Okay. Thank you very much.
Yeah.
So I don't see any more question coming. No, there is one question.
Okay.
Rajanandan Chaudhary, you have shown a picture of the experimental control system at the beginning of the lecture. What is the typical cost of such systems? How much time does it take to build them from the scratch?
Yeah, so this one took a good question. This took many years. So I think we constantly building. We are constantly working on the experiments. We constantly keep upgrading them and improving them. And this one, I don't know, it took like 4 or 5 years to build. And I guess right now, if you build something like this, you are probably in the €2 million range, $2 million range.
Okay, so Professor Bloch, thank you very much for the excellent talk. I am sure that all of us enjoyed this talk. So we'll see you tomorrow, the same time.
Yep.
Okay, for the second talk.
Looking forward to it. Have a nice day, everybody. Bye, everybody. Bye.